There.
10%.
10%, 0.1, right? That probability transmitted will be 0.1, right? It's given there, right? Just you put the probability there, make sense? If it's 20%, then it will be 0.2. In that case, it's there. User has only 10% of the time. That's a probability, okay? Now, remember, our objective is I try to show you how to get the number like this. Make sense? That's basically somehow I want to show you how to calculate this number. Those are given. Everybody okay, right? Now, suppose there are 120 users. Suppose that's an ISP, right? 120 users paid for it. We have 120 users. Actually, they can support 20 users, active users at the same time, right? If you are second switching, basically even at the same time, we can only support 20 users, right? So find the probability that at any given time, exactly a user transmitting simultaneously. That will be what? Just a very simple binomial transmission, right? You have a total 120 users. At the exact time, remember your P is 0.1. You put a P there, right? Later on, you just put a 0.1, change it. At the total users 120, given any time, a user transmitting at the same time, that's basically the formula. Make sense? That's just definition of binomial distribution, right? Make sense, guys? Everybody okay with this, right? So in that case, if it's one user transmitting, the probability is just 120. The n is 1, right? And substitute P is 0.1. 1 minus P is 0.9, right? Make sense? So then go on. When do we have problem? When we have problems, when we have more than 20 users transmitting at the same time, right? Make sense, guys? Then from this formula, you can know, okay, 1 user, 2 user, up to 20 users, we are all fine, right? So in that case, given those from 1 to 20, what's the corresponding probability? You can use it to do the calculation, right? Make sense? Those are all time, all fine, except when there are more than 20 users transmitting at the same time, then you have a congestion. Make sense? Then basically you can do the calculation now, right? What would be probability? There are 21 or more users transmitting. Just 1 minus 1 user out to all the 20 users. You have a summation. Make sense? Got it? That's basically how to do the calculation. Basically, it will be this equation. Got it? Right? Regarding to how to do the estimate using the central limit theory to the estimation to calculate this, I don't care. But you understand this concept, how to do the calculation there. Make sense? Guys, 1 minus, when you have 0 user, 1 user, up to 20 user. That's basically you can calculate the probability. If you calculate the previous case, that's basically the 35 user, more than 10 users are using, that's basically 0.004 light is come from. Similar calculation, got it? Clear, right? So if I put the number small, you don't need the central limit theory, but you understand the concept, you can do the calculation, right? If you know this, one of the homework is similar, just testing your understanding regarding to this. Make sense? You understand when do you have problem and what's the benefit of packet switching? When does packet switching has a congestion? How to calculate the probability? Make sense? Got it? So for this central limit theorem, not required. You as long as you understand this, it will be fine. Got it? Okay. This is one of your homework there. Okay. Another quick one. Then I think now, if I ask you again, packet switching and circuit switching, you got the basic concept now, right? Right? You kind of appreciate why the internet is based on the packet switching, not the circuit switching, right? Because we want to service more users, right? More users. And each user, they are not like just say there, I want to access the internet all the time, right? We want to use on demand. Make sense? That's basically circuit switching kind of. Okay, check this one. So there's one method bit per second link. We have 10 users, and one user generates a huge data, right? 1,000 bit, 1,000 K, just 1,000 megabit, okay? Packet. While others do not, other users are silent or silent or just doing nothing. So if you're using the TDM, time division multiplexing, which is circuit switching, right? If you're using TDM, if it's TDM, we have 10 slots per frame. Then how long it will take to deliver this packet, guys? In that case, what should we do, guys? Just quickly tell me if you can. Still, we have L divided by R, right? If you are doing the TDM, what will be the R?
What will be the R?
So, I'm just asking you to answer this question. Oh my problem is to remember the name. So first tell me what will be the R?
10.1 Mbps.
1 megabit per second divided by 10 because we have 10 slots, right? That's the R. Then L is 1 megabit, right? Just the L divided by R. In that case, just what is the new R here? Make sense? Then you do the calculation, okay? Each user, I guys agree? Basically, because we have TDM, so basically we have a whole bandwidth, then you have subband, right? Available, the R would be 100K bit per second, then L divided by R, then 10 seconds, right? You did the calculation. Now, no TDM, right? Now it's a circuit switching. What will be how long it take to deliver the packet? It should be easy, right? It's now not a circuit switch anymore. It's packet switch.
Yeah. So you don't have to divide by 10.
One second.
The reason is there's some assumption. The reason is others should not generate packets, right? Basically, other users are lazy. They're sleeping. Only you're working, right? Make sense? In that case, the whole channel is yours. What will be the R? The R available to you still the 1 megabit per second. Make sense?
Yeah.
In that case, the L is still the same. This is still your L, right? The R is this. Got it?
Yeah.
It's 1 second. And if you're using circuit switching, 10 seconds. Packet switching is 1 second. But the assumption is the other people are crazy. Got it?
Yeah.
That's basically sometimes if the network is kind of just is underused, you can take advantage, perform the things much quickly. Makes sense? But if the network is congested, it will be totally different story. Make sense? This for everybody. Okay. So we can pass. Okay. Then remember, today we just watched the video. Remember when we start this class, I asked you what is the internet, right? Then we call one of the answer is what they call is both and from an architecture, kind of approach is network of networks, right? Then from the basic architecture perspective, think about it. Every people, when you try to access the internet, each people, you're somewhere here, right? Make sense? You use different access technology. You pay your local ISP, then you access the internet, right? If you are at per bill, you have the institution network. You are maybe using the Wi-Fi or something, right? If you are some relatively far away, you may be using cellular network. If you're at home, maybe this is your home network, but you're paying local ISP to access the internet. Makes sense? Each user connect to all kinds of different access networks. Makes sense? But eventually, the internet, somebody say the internet is the biggest network. Do you agree? It's not one network, right? You just need to collect multiple millions network together, okay? you have all kinds of different network on that. We need to connect them together. Okay? But how to connect them together? That's another story. If you're doing this kind of, this is kind of too complicated, right? And not scalable. Make sense? That's why we have a multi-level of ISPs. We have regional ISP, we have tier 1 ISP, we have tier 2 ISP, right? Make sense? If you only have one global ISP, then that's a problem. It's a monopoly, right? Make sense? We need competition. That's basically we need multiple tier 1 ISP. Then in some area, they only do not have tier 1, they maybe have the regional, right? They have a multi-level, multi-hierarchy to connect together. In order to actually give us the feeling is everybody can talk to everybody, right? That's why I make the internet kind of powerful, right? Make sense? You guys watch this. So some of the keyword is then the content provider network is also recently is really powerful, right? Makes sense? Like the Google, like Amazon, like Google, they have their own private network. Regarding their private network architecture, they also have their specific technology in there, okay? So plenty of the new things are in there, but you kind of hopefully understand those kind of architecture in there. So everybody is kind of closer to here, okay? Regarding to think about it, think about your case is you want to talk to a friend somewhere, okay? You need to trace up, then trace down. You need to first access the internet, right? Your local ISP need to connect to some kind of tier 1, depends where you are. Maybe just regional, then they need to connect to your another user there. Makes sense? Think like a tree structure in there. Just to think about. That's why along this you might have a multiple hops along this way. Then another more important way that also mentioned some key concepts, right? Like peering. Makes sense? You guys, when you watch the video, you guys notice, right? The ISP, something, just later on if you're interested, chapter 2, we may revisit some of the more important application in there. But if you have questions, you can rewatch those videos, okay? Like internet exchange point, because eventually, money is important, right? Right, makes sense? When you pay your monthly fee to a certain company, but actually only, for example, I'm using the AT&T to access the internet, okay? But your friend may be using another ISP, right? Makes sense? They are paying another company. So eventually, everybody needs to talk to everybody. Right? You are paying monthly regarding how, but at the same time, nobody is patient. If you cannot talk to you instantly, you cannot pass on, so now you think the network is broken, right? That's basically what's happening. Makes sense? In order to make all the transition smoothly, all the big ISP, they need to have a financial agreement. That's called peering. Makes sense? Mm-hmm. They are take advantage of each other's network in order to make the packet smoothly pass on from each user to everyone. That's why the internet is powerful. Okay, lots of financial agreement is in between. That's why they feel we can do everything through the internet. Okay, that's the hope you can understand a little bit later. Then we talk about the data center is one thing. Regarding to content provider network, the private network is also really important in recent years. Okay. See, that's another way to show the tree structure. Local ISP. If I want to talk to somebody here, think about how those kind of hubs might go through. Make sense? Right? Okay. So we're done with network core. This part is important. So next section we'll talk about the performance. Okay. performance, talk about what is loss. We already mentioned that in the routers, QE. If the queue is full, you may have loss, right? We talk a little bit about the delay. So far, you guys already heard about what? Transmission delay, latent transmission delay. You also heard about the latent queuing delay, right? Then we have two more other delays there. Then we will talk about the throughput. Okay, makes sense? So if your check, remember, homework mine is there. We will have midterm, some of it. Those sections are relatively easy to give you exam questions because it's quantitative. Makes sense? I will still ask you to watch first. Then we will have a quiz number 2. Okay? This section is still kind of important. Still important, okay?
Get mechanic training at Universal Technical Institute and learn the skills needed to In our discussion of the network core, we saw how packets can be delayed or lost at routers within the network. In this section, we'd like to take a little bit of a deeper dive into the issue of performance. We'll start off by looking at delay a little bit more carefully, looking at the different components of delay. We'll look at a tool called traceroute, which will actually allow us to measure and look at real delays in the live internet. And finally, we'll wrap up by introducing a new performance metric, that's throughput. So, why don't we get started? Recall that we learned in the last section that packets queue in router buffers, waiting for their turn for transmission. We also learned that packet queues grow longer at a router's output link when the arrival rate to that link, hopefully just temporarily, exceeds the output link's capacity. And we learned that packet loss can occur when the memory needed to hold packets fills up. Let's now dive deeper into 4 components of delay that can happen at a router. And the first of these components of delay are what we might call a processing delay. This is the delay associated with forwarding table lookup, forwarding a packet through the switch, and doing some associated integrity checks. These delays are on the order of microseconds or less. The second component of delay is the queuing delay that we saw in the previous section. This is the amount of time that a packet has to wait to queue at an output link for transmission. And as we saw earlier, the amount of time spent queuing and waiting for transmission is going to depend on the congestion level for the outgoing link. We also saw earlier that once a packet begins transmission, it's being sent into the link at transmission rate R, it takes a certain amount of time for all of the bits in those packets to be pushed into that outgoing link. This is known as the transmission delay, and as we saw earlier, transmission delay is simply the number of bits in the packet L divided by the transmission rate R. And finally, there's propagation delay. This is the amount of time it takes from when a bit first enters the sending side of the link until it pops out at the receiving side of the link. Now, bits generally propagate through media at close to the speed of light, and so you might think that's fast, but in fact, you can actually notice propagation delays. For instance, the amount of time it takes from a bit being transmitted on the Earth up to a geosynchronous satellite, 270 milliseconds. For a transatlantic link, the delay from one side of, say, the east coast of the United States to Europe, that's on the order of 30 milliseconds. And these delays can actually become quite noticeable. So, there you have it.
Guys, I'll give you guys the quizzes for later. Make sense? You need to watch it, get it, then do it. Just I want to save time. This usually not like you to do it right now. Does that make sense? Make sense?
Components of delay: the processing delay, the queuing delay, the transmission delay, and also the propagation delay. Now, I found that sometimes students confuse transmission delay with propagation delay. So let's look at that just a little bit more carefully, and let's start by using an analogy. As always, a real-world analogy might help here. Let's consider a caravan of cars. Cars are the bits, the caravan is a packet, and taking a toll and passing a car through a toll booth is like transmitting a bit. A car then drives, that is, propagates onto the next toll booth. And here's the question we want to ask ourselves. How long is it until the last car of the caravan leaves the first toll booth before the entire caravan is lined up before the second toll booth? In order to calculate a numerical example, let's make a couple of assumptions here. Let's assume that the toll booth takes 12 seconds to service a car. That's equivalent to a bit transmission time. And let's assume the cars propagate at 100 kilometers per hour. It's like a bit propagating through the medium. And finally, let's assume that the toll booths are 100 kilometers apart. Well, with these as givens, we can compute the time to push an entire caravan through the toll booth and onto the highway. Well, it's 12 seconds per car. There are 10 cars per caravan, so that's 120 seconds to transmit the caravan, if you will. Now, let's look at propagation delay. The time for the last car to propagate from the first toll booth to the second toll booth, well, it's got to go 100 kilometers. It propagates at 100 kilometers per hour, so it takes an hour for that last bit to propagate from the first toll booth to the second toll booth.
You guys like this example? It's kind of the time scale wise is different with the actual data transmission, but it's good for your understanding. Makes sense? In reality, guys, remember, so far transmission delay is what, guys? What's the formula for transmission delay? L divided by R. In that case, for example, what is in this case L divided by R for each packet? What's the corresponding transmission delay in this case?
Service 12 seconds.
Yeah, 12 seconds. For each packet is 12 seconds. Makes sense? That's the basic transmission delay in this case. Similar, think about when you want to push it out to the next your transmission part. So because we have 10 cars, let's make the 10 multiply L divided by R is 120 seconds. Then what is the propagation delay? You guys remember the formula for the propagation delay is what?
Distance by S.
D divided by S, right? D is the distance, S is your propagation speed, right?
Yeah.
Typically, when we talk about the kind of communication is close to what? Light speed, right?
Yeah.
So in that case, in reality, like for example, even Houston people talk to Houston people, the D is too small. Only when the thing is getting significant is, for example, you talk to people in China, you talk to people in Europe, where you have to go through the, under the ocean cable, or you go to the satellite link, the D divided by S can become more significant. Make sense? That's basically, but in this case, because it's through the car, although the 160 miles, something around there, it's not that far, but still the S is too slow. That makes the propagation delay more significant. In reality, its transmission delay is more significant. Make sense? The concept is important, but you understand that you need to drive the car. The packet actually need to go through the electromagnetic waves, go through those actual physical channels there. That's basically the propagation delay. Make sense? Only the scale wise is slightly different in this scenario. Okay?
So in total, the total amount of time it takes until the caravan is lined up before the second toll booth, 2 minutes, that's the transmission time.